Hello and welcome back to another video in our continued journey of trying to master geometry. And our today's agenda is going to be further work on circles and some properties of secants and tangents. So before starting this video, I'm assuming that you're familiar with some basic properties of circles and chords and tangents, etc., which we have already covered in previous videos, and we'll try and build on from that point onwards with some new theorems and new observations about chords and tangents operating around a circle. So let's start with a quick recap of a couple of ideas that we'll be using today to further derive new ideas. And one of them is about angles subtended by a segment or a chord at the circumference and the connection with the angle at the center. I know if this angle is x, this angle is going to be 2x. We learned this earlier. We also learned that if I create any other angle on the circumference from the same segment or the same chord, all of them are going to be equal to each other and all of them are going to be x. So this is one idea that we'll be using to derive our results today, and the other idea that we'll be using a lot is basic similarity. That if I give you that two triangles ABC and say DEF are similar to each other, the ratio of the sides are equal. So AB, ratio of corresponding sides is equal. So AB upon DE is equal to AC upon DF is equal to BC upon EF. If we are comfortable with these two results, whatever else we work on today will be derived from here. So understanding that would be fairly easy. If you don't know these results, my suggestion, and both of them, my suggestion is first mastering this idea and then starting with this video. Because even though we are talking about circles, most of the properties and the theorems that we'll be using will revolve around angles and triangles, etc. So it helps if you are very good at this, because then you will see that whatever we are learning today is nothing but just extending this idea one step forward. So our first observation of the day is going to be about chords, two chords intersecting inside a circle. And what can we say about that? Let's say a very standard question could be something like this. If this is 3 and this is 4 and this is 6, how much is this going to be? And the idea is very simple. I'll just introduce the idea first, then we will work the logic out. The idea is that 3 into 4 is going to be equal to 6 into this. So say this is x, 3 into 4 is equal to 6 into x, right? You want to give it names A, B, let's say C, D, and let's call this point intersection I. So the theorem is that AI into IB is equal to CI into ID. So using this, I can work out this value very easily. This is going to be 2. So this is straight away I'm applying the idea, but first we want to understand that why is this happening. So let's try and work on that. Let me draw this diagram again, and let's say the two chords are intersecting. So name them A, B, C, D, and let's say I. So what I'll do now is I will connect this C to B and I'll connect this A to D, and I will use the same theorem that I started the day off with, that if I have a segment subtending two angles at the circumference, those angles are going to be equal to each other. So for example, if I think of the segment AC, the segment AC is subtending this angle B. The segment AC is also subtending this angle D. That means this angle is going to be equal to this angle. You can name them also something. X is equal to X here, right? Now change your point of view. Think of the segment DB. It is subtending an angle C here. Call it whatever you want to. This angle is going to be equal to this angle, because again the same theorem, a segment or a chord, when they subtend any number of angles at the circumference anywhere, all of them are equal to each other. So when I take this point of view, these two are equal to each other, and when I take this point of view, these two are equal to each other. What now? And obviously these two angles are equal to each other because they are vertically opposite angles. So essentially what I'm getting is that in these two triangles, all three angles are equal to each other, and therefore immediately similarity kicks in. So say I use the triangle AID, and then I map the corresponding angles. For A I will have C, for I will have I, and instead of D I will have B, right? I hope you do the work along with me and not just follow the voice, right? And then the similarity kicks in, the basic idea that the ratio of corresponding sides, that is AI upon CI, is equal to ID upon IB is equal to AD upon CB, right? Use this idea and you see that if I cross multiply here, I get AI into IB and CI into ID using these two, and therefore proven. Now you also have the proof, and you're kind of also revising similarity. So instead of thinking of it as a proof, think of it as a similarity practice problem, and that's it. So this is the proof. You're using similarity and this idea, and this is the application, something like this, that this part will be given, this part will be given, this part will be given, this part will not be given, or three parts will be given, one of them will be missing, or this result will be used in some other story, but essentially understanding that this part into this part is equal to this part into this part in your own language. Staying with the very same idea of two chords intersecting each other inside a circle, we have another very interesting result, and it will be something like this. Let me start with the problem statement first and then work on the proof again. So the story given to me will be that AB and CD are two chords, and then I have the center of the circle, let's say O, and this angle will be given to me. Say this angle is 35 degrees, and this angle will not be given to me, say this is X degrees, and it will be given to me that this angle AIC is going to be 30 degrees. So how will I work out this problem? Once you know the formula or the theory is going to be ridiculously easy. Very simply put, this 30 degrees is equal to half of 35 degrees plus X degrees. And now let me try and verbalize the idea. This angle created by the chords intersecting, obviously this angle and this angle, they are going to be equal to each other, but the angle created by the chords intersecting each other is equal to half the sum of the angles created by the segments at the center. So if such a story is given, I can use this result. So the result is very easy. Now let's try and understand why is this particular relationship happening. Why is this angle equal to half of this angle plus half of this angle, right? And again, the clue is already there in the only theorem that we've been using over and over again. If I think of the angle at the circumference, this is x and this is 2x. So the angle at the circumference is half the angle or angle created at the center by the segment, right? So I'm going to use the same idea again to derive this particular result. As of now, we have straight away looked at a problem, but now I want to understand it a little more theoretically. So let me draw this diagram again. So let me make a bigger diagram and let me draw the chords, name them also A, B, C, D, let's say I, and the center point is O. And now I create the angles, right? The segment AC or this particular chord AC creating, let's say, call this angle X for a second. And similarly, this segment DB creating an angle Y at the center. I want to know why this angle AIC, is equal to half of X plus Y. Perhaps you can hit pause and try and work out this by yourself. You might have to draw a couple of lines here and there, but it is always a good idea to try and challenge yourself first before looking at any kind of solution or discussion. So let me think of the ideas now. I already have a very big clue in terms of the previous theorem that is being used. This angle created by this segment at the center is X. Now if this segment creates any other angle on the circumference, it is going to be half of x. So that is my hint that I already have. So let me see, where is this segment creating an angle? I see it is not happening anywhere. So let me connect C to B. Let me make it thicker only. C to B. And keep your orientation, look at it from this side. This segment AC now is creating angle ABC at the circumference, and this angle is going to be half of this angle. This angle is going to be half of x. And the y, hopefully we already know, like we have already looked at it 15 times, right? Similarly, now I change my point of view and I think from the segment DB, the segment is creating an angle y at the center. Where else is it creating an angle? I already have the line now. DCB is the angle at the circumference. So if this angle is y, this angle is going to be y by 2 or half of y, right? And now focus on this triangle. And hopefully you are making your own very neat, very colorful diagrams. This is a triangle. I know this angle is y by 2 and this angle is x by 2. This angle is the exterior angle of this triangle. If I extend this side, this is the exterior angle. And what do I know? My basic property, that the exterior angle is the sum of the opposite interior angles. From triangles day 1, from triangles and angles day 1 theorem, right? So this angle is going to be this plus this and you're done. So angle AIC is going to be angle this plus angle this. Angle ICB and angle IBC, which is y by 2 plus x by 2. And you're done. So half of x plus y. And how we used it in the question, we already saw earlier. Now the very same idea in a slightly different context. We are still thinking of two chords, but this time they're not intersecting inside the circle. Say they will intersect outside the circle at some point, somewhere, and let's call this point I again. And say the chords are AB and the chords are CD. So once again, I have the same result, exactly the same as before. AI into BI is equal to CI into DI. That means this distance into this distance is going to be equal to this distance into this distance, verbalized in your own language. And the result is exactly the same as before, just that the visualization is different. So again, a very simple application would be something like this. Say this is 5 and this is 3. And it is given to you that this is 4 and the question is how much is this? A very easy version of the question. So we want to look at AI first. AI is A to I, that means 5 plus 3. So AI would be 8. BI is very, very simple, straightforward, it is 3. CI, I don't know right now, it is going to be something 4 plus x. If I am calling this x, it is going to be this whole thing. So 4 plus x and into DI, which is 4. Actually, it can be done without writing this equation sort of a thing. This is 8 into 3, that means the product is 24. 8 into 3. And this product is also going to be 24. 24 is equal to 4 into something. So what is that something? I can very quickly figure out that something is 6. But once again, the whole thing is 6. This is 4, so therefore this will be 2. Or you can solve this equation. So exactly the same theorem as before, and this is an example or a very basic application of how it gets used in a question. But now once again we want to figure out why this is working, what is the logic behind it. And again you will see as we work out the logic using whatever theorems we already know, those theorems will get revised, as well as I can look at these as problem challenges itself, proving this particular thing, right? So you can start thinking and maybe connecting it, so will help with the ideas. So using the same diagram, forget the story of the numbers for a second. So let me draw the diagram once again. Same story, two chords A, B and say C, D, and extended outwards, and they intersect at I. And once again, I want to understand the result. AI into BI is equal to CI into DI. Why is this true? And while we do so, a couple of things will get revised, right? So what I'll do is I will connect AC and I'll connect BD so. And then what I can and say if this angle is theta, I can say this angle is also going to be theta. And once again, the question would be why. So if I look at the figure ACDB, it's a cyclic quadrilateral. In a cyclic quadrilateral, the sum of opposite angles is 180 degrees, something that we have done in basic circles. So theta plus this angle, if this is x, theta plus x is going to be 180 degrees. Theta plus x is 180 degrees. So what is x? X is 180 degrees minus theta, right? Say I want to figure out the value of y. I know x plus y is going to be 180 degrees. Why? Because it's a straight line. So x plus y is equal to 180 degrees. What is x? X is 180 minus theta. So I'll put a 180 minus theta here. The 180 will get cancelled and y will be equal to theta. Please work this process out for yourself. So therefore I can say if this angle is theta, this angle is also definitely going to be the same. The reason being cyclic quadrilateral. Using the same idea, say this angle is sigma, this particular angle is also going to be sigma. Why? The same idea, this angle plus this angle, whatever, call it z for a second, is going to be 180 degrees, and this angle plus this angle is also 180 degrees. Therefore this angle is equal to this angle. Do work out is the same proof applied from a different angle. And now if I think of triangles, let's say BDI and the triangle ACI, once again I have similarity playing out, because in this triangle and the big triangle you have two angles which are equal to each other. The third angle is common anyway, and therefore the big triangle is similar to the small triangle. So now let's just map the similarity and the proportions, and then we'll see the result immediately. And if you have done the previous proof, you already know where the story is going, right? So I think of the big triangle, let me call it triangle ACI, and then I will map it. A corresponds to D because they have the same angle, right? So instead of A, I will write a D. C corresponds to B, so I'll write a B, and I is common. And now I will write the proportionalities. AC upon DB, AC upon DB is equal to CI upon BI is equal to AI upon DI. I wanted AI into BI, so if I use these two, AI into BI is equal to CI into DI, and now you have the proof. And you have this interesting result also, that if you create such a story where the two chords are intersecting outside the circle, and you create this angle and you create this angle, you know they are going to be equal to each other, or this angle is also going to be equal to this angle, which is another handy result, can be applied in another problem. So this a mirror copy of an idea that we have done earlier. Same story again, the two chords are intersecting outside the circle somewhere. Name them A, B, I, C, D, I, and I will focus at the center this time, and I will think of the angle created by the segment AC at the center, let's say call it O. And similarly the angle created by BD at the center, angle BOD. And I want to connect this angle. So this is a copy or the alternate mirror of this theorem, where we looked at the angles created by the arc at the center. If I call them x and y, this particular angle was half x plus y. So I want to this time figure out what is the relationship of this angle to these two angles. So let me once again call them x and call them y. And again, I know the theorem that I am going to use, that the angles created by a particular segment at the circumference are equal to each other, and they're half of the angle created at the center. So if this is 2x, any of these angles is going to be x. So I know the angle created by AC at the center is AOC, Now let me see what other angle is it creating on the circumference. This angle, angle ADC, is also created by the same segment. So if this angle is x, this particular angle is going to be x by 2. Similarly, if I think of the segment BC, it is creating this angle y at the center and it is creating this angle DAB at the circumference. So this angle is going to be y by 2. And now focus at the triangle ADI. If I say this angle is x by 2, this is the exterior angle for the triangle. So x by 2 is equal to the sum of these two angles. Let's call it z for a second. So x by 2 is going to be y by 2 plus z. I want to figure out the value of z, right? So z is equal to x by 2 minus y by 2, or overall I can say half of x minus y. So in this story, this particular angle was coming out as half of x plus y, and in this story where the angles are meeting outside, this angle is coming out as half of x minus y. And otherwise the idea is almost identical. The connection between the angle created by the intersection of chords compared to the angle created at the center, whether it's happening inside the circle or outside the circle. And once again, a very standard or let's say ridiculously easy question would be, this angle is 40 degrees, this angle is 50 degrees, how much is this angle? So very easily I want to do x minus y, right? So 50 minus 40, 10 and the half of that. So this angle is going to be 5 degrees. Or maybe this angle would be given and this angle would be given, and you would be asked a question about this particular angle, and I can use the same idea and figure out, and I know the value already, but this is how it would play out in a particular question. And of course this could be a smaller idea playing out in a bigger question, as we'll see in a couple of minutes. Okay, so now let's try out a couple of questions based on these ideas. So this is the story given to us. AOB is the diameter of the circle which is extended to point E where it meets the chord CD. And it is given to me that angle AOC is equal to 50 degrees, angle AOC is equal to 50 degrees, angle AEC is equal to 15 degrees, angle AEC, this angle is equal to 15 degrees. And the question is, what is angle BOD? I have to find this angle, angle BOD. So the moment I look at this figure, forget about this being a diameter, that is just a digression in the story. This is a chord, diameter is also a chord, this is a chord, and they are meeting at point E. And we just learned that this angle, say if this angle is x and this angle is y, I know this angle is going to be half of x minus y. I know this is 15, so I know 15 is equal to half of x minus y. I also know x, angle AOC is equal to 50 degrees. So I know this is equal to 50 degrees. That's it, I just have to solve this equation. This 2 goes here, so I get 30 degrees is equal to 50 degrees minus y. And therefore y is equal to 50 minus 30 or 20 degrees. So this angle is 20 degrees. So if you know this particular idea that when the chords are intersecting, this angle is the result, or this angle is half of this angle minus this angle, you can do this question in no time. But if you are not aware of this idea, this question can also take up 5 minutes of your time, depending on how long you take to work out this particular result. Because even if you don't know it as a theory, you can still try and play and derive the same on your own as a problem challenge as such. But if you already know this idea, such kind of a problem will be done in no time. Another problem from the exercise, and by now this should be ridiculously easy. In this figure, it is given to me that angle AOD is equal to 100 degrees. So this angle is 100 degrees. Angle BOC is equal to 50 degrees, and the question is, what is angle APD? I already know the idea. This angle is going to be half of this minus this, So 100 minus 50 and divided by 2. 50 divided by 2, 25 degrees is my answer. And it took all of maybe 10 seconds. Provided I know this idea, I can spot this quickly, and this problem is very, very easy afterwards. So let's try one more problem. At least this one looks slightly different, so it might be a little more fun, because the last couple of questions were very, very obvious. So this is the story given to us. This is a semicircle. AOB is the diameter. It is given to me that angle DOC is equal to 80 degrees. Angle DOC is 80 degrees. And the question is, what is angle DEC? What is angle DEC? So, of course, when I see a semicircle, I might start using the other property that in a semicircle, if I draw any angle, that will always be a 90-degree angle. But we will try and do this question without using that property. I don't even know whether this will work or not. I still want to look for the idea of intersecting chords and the angles that they are creating. So for example, if I think of the chords DB and AC, they are intersecting at E. So this angle I know will be half the angle created by the segments at the center. Half the angle created by the segments at the center. I am using this idea, the theory that we just looked at right now. This is the center. This segment, let's say if it creates an angle X and this segment creates an angle Y, I know this angle or this angle is going to be half of X plus Y. So same idea, imagine the full circle to be there, it doesn't matter. These are two full enough chords for you. This is where they are intersecting. So now I am thinking, okay, where is this angle dropping? So I see this is the angle, let me call it X for a second. And then I look at the other segment and I see this is the angle, let me call it Y for a second. And I know this angle is 80 degrees. I also know that sum of all angles in a straight line is 180 degrees. That means X plus Y plus 80 is equal to 180 degrees. So X plus Y is equal to 100 degrees. So I have a measure of X and Y, and remember all I needed was half of X plus Y. I don't need to know individually what is X and individually what is Y. I know this angle or this particular angle is half of X plus Y. I hope you can see the same diagram playing out here. So I know X plus Y is 100, half of that means this angle is 50 degrees. These two angles are vertically opposite angles. So if this angle is 50 degrees, this angle also will be 50 degrees. And now I will go, the sum of all the angles at this point is going to be 360 degrees, a whole circle, right? 50 degree, 50 degree, 100 degrees gone. So out of 360 degrees, you are left with 260 degrees. And again, this angle and this angle, they are equal to each other. If this is A, this is also A. So 260 degrees is equal to 2A, and therefore A is equal to 130 degrees. So perhaps because it looked different and you might have to spend some time to figure out where are the segments, where are the angles dropping, and then spot that X plus Y 100 is enough for you to figure out this. And then immediately you're not getting the answer, because from the total story you remove this and then get to this point. So a little bit of effort, but a very good application of the idea that we learned earlier. One last circles questions to wrap up this session, and this question has nothing to do with the theory that we just looked at right now, intersecting chords or angles or anything. In fact, you will not need any big ideas to solve this problem. Let me state the problem first. There is a circle given, C is the center. It is given to me that CB is equal to 7, so this segment is 7, and BD is equal to 4. And the question is, what is the length of the rectangle AB? So this is what your question is. And maybe at this point you should hit pause and try out the question, so that you can appreciate the idea that a lot of times the question might look very, very scary, and you might start going into very complicated ideas, but start with your basics first and then see what clicks. So I hope you tried the question, and if you found the answer, then it's ridiculously easy. This is 7 and this is 4, so I know the radius is going to be 11. And radius means the distance of the center from any point on the circumference is the same, right? That means this distance is also going to be 11. let me call it x for a second, Cx is also going to be 11. In a rectangle, the diagonals are equal to each other. So if this diagonal is 11, this diagonal will also be 11, and you are done. So a very simple question if you can spot this idea, or you might end up, as I've seen a lot of people try and apply a lot of very complicated theory. They will still get the answer, but the workaround is so much. But if you can spot this idea, your question will be done in no time. So this is it for this session. Just a couple of very simple theorems and ideas related to chords intersecting inside a circle or outside the circle. And just repeat the proof a couple of times for yourself, do it on your own, and then the idea will become very familiar to you. And let's say when you encounter a related problem, the response time maybe will be slightly faster. So this is it. In the next session, we'll look at the tangent second theorem and a few problems related to that. And then we will try and move towards the plain problem solving and a lot of practice related to such ideas. So see you soon.